closed set. So we have considered open set in our last class. We consider closed set now. We divide closed set. We say that a set A is closed if it contains all its limit points. So this set of all limit points, derived set that we have given. So derived set, if it's a subset of A, then we say that A is a closed set. So we set of real number and empty are both closed. In fact, they are both open too, because real number contains all its limit point. Empty set, there is no any point there, so it's automatically open and closed. So this one to contain all its neighborhood. So all its neighborhood is a neighborhood of all its points. In that case, it's open. So they are both open and closed. Now, let's consider a theorem. Our theorem 1. Set A is closed if and only if its complement is open. So this theorem is a theorem, is also a definition. Some people will use it as definition. So this is another definition of closed set. We say that a set is closed if and only if its complement is open. And it's also a theorem. So, and what that statement is saying is that if set A is open, then A complement will be closed. And vice versa, if A is closed, then A complement is open. So let's prove the theorem. So the first thing to do is that we need to show that if A is closed, then A complement is open. Now, let A be a set and A complement be its complement. We assume that A is closed, then we need to prove that A complement is open because of this if and only if. So we are going to prove it in two ways. So that we first assume that this set is closed. Then if the set is closed, then we must assume that A complement is open. Now, we are dealing with this. So let's pick a point inside this place. So let S belong to A complement. So this will imply that S does not belong to A by the theory of set. By set theory, we know that if S is not in A complement, then if S is in A complement, S will not be in A. So we have known this already. Now, since S does not belong to this, it simply means that S is not the limit point of A. You know that if a set is closed, it must contain all its limit point by definition. But here, we said that S is not in A. But here we have said that we have assumed that A is closed. So if S does not belong to this, but A is closed, it simply means that S is not a limit point of this. Then by definition of limit point, this is the definition. We say that if S is not a limit point of A, there is a neighborhood N of X such that N intersection A is empty. So here we have seen that S is not a limit point of A. So by definition, so we cannot say that by definition there exists a neighborhood N of X such that N of X intersection A is empty. So that is what we showed here, what we just showed now. Since the reason why we wrote this is because of this this fact that S is not a limit point. So this is what we are going to have by definition. And this, if you look at this in a normal way, in a normal set theory way, N intersection A is empty. This simply means that N cannot be a subset of A. Because if N is a subset of A, their intersection can never be empty. They are disjoint. So that simply means that this neighborhood can never be a subset of A. So if neighborhood can never be a subset of A, then it must be a subset of A complement. So, and this thing simply means that S belongs to the neighborhood and is a subset of A complement. And if you remember, this is definition of open set. So since we have this, we can now say that this last one here, each complement is an open set. So we have shown that when A is closed, then A complement is open. So we have shown it. Now we need to show the other way around. So conversely, if A complement is open, so we need to prove that A is closed. So let us take a point from this A. So we have picked the point in A. So that point will be a limit point of A. So because A is closed, so let S be a limit point of A. So we know that S will never belong to A complement. So let's now prove by contradiction. Contradicts our assumption. So hence S belongs to A. So hence we cannot say that A is closed, and that completes the proof. So let's consider another theorem. Another theorem here. Every closed interval is a closed set. So we need to let this be a closed. For us to show that this closed interval is a closed set, so we only need to show that the complement of this closed interval is open. Suffices to show that the complement of this is open. And why are we choosing that? Because we have said that if a set is closed, then its complement must be open. So that means for us to show that this thing is open, we only need to show that the complement is open. Now, if you consider this, let's say this is closed interval A and B. So the complement, this is a real line. Let's say this is a real line. This is minus infinity to infinity here. So this thing can be written as this minus infinity to A is an open interval union. This thing is A to B union B, this is a B comma infinity. So all of them are real numbers. So this is the union. So that means the complement of this will be union of these two. So in that case, I can say that A close interval A comma B intersection is complement is equal to this interval union this interval. But is observe that this is open interval, this is open interval. So, and we have said before that every open interval is an open set. So that means this is an open set, this is an open set. And we said that the union of two open interval is also open. So that means everything here will be equal to open. So that means the complement here is open. So we write it in statement as, since every open interval is an open set or is open, and the union of two open sets is open, not two open interval, two open sets is still an open set. So hence this thing is open. So this complement is open, and then we cannot conclude that this is closed because its complement is open. Definitely this one will be closed, and that completes the proof. We have another theorem here. The union of finite number of closed sets is closed. That is also closed set. So we start by getting the collection of closed sets. So let this be collection of closed sets. So it will be finite closed set. That's why we put I runs from 1 to n. It's finite. The collection of closed set, finite closed sets. We want to show that their union is also a closed set. Now, by our theorem 1 there, so we only need to show that the complement of this thing is closed. So we only show that the complement of this thing, is open. So if you find the complement, let's find the complement. A complement is equal to this. It will equal to this. I'll put a complement to both sides. So if you remember from the Morgan's law, which says that A union B or complement is same thing as A complement union B complement. So this thing will just be it's intersection. Sorry, so it will be intersection. So I'll put the complement on only high. So the union will turn to, so this is by De Morgan's law. So this is by De Morgan's law that the union will turn to the, so and to the intersection, and this complement will be on this thing. Now we cannot say that so since each AI is closed by this, we have said that let it be a closed set. So since each of this is closed by our theorem 1, then if you put complement of this, each of this will be open. And by our theorem in open set, we say that intersection of finite number of open set is open. So we write it out as, and the intersection of finite number of open set is open. So you can say intersection of, this thing is open. So intersection is open. So hence, that intersection we are talking about is open. So the intersection is open. This simply means that A is equal to this is open. And if this is open, the complement is open. So definitely A is closed. And that completes the proof. So we can have another one. We can say that the intersection of arbitrary union of the arbitrary number of closed sets is closed. So let's consider the theorem. The intersection of arbitrary number of closed sets is closed. So let's prove it by saying that let AI be collection of arbitrary closed sets. So what do we want to show? We want to show that their intersection is still closed. So it suffices to show that the complement is open. So to show it, we only need to find the complement. If the complement can be open. And remember from De Morgan's law, we say that A B complement is A complement union B complement. So that means this thing will become this. I belongs to this AI, then it will be on the A. That is by De Morgan's law. So it's equal to this. So we can now also say that since each AI is closed, AI complement will be open. So by our theorem 1, and we know that the arbitrary union of open set is open. So definitely this A complement, which is this, definitely our A complement, which is this, is what? Is open. And if this thing is open, definitely this will imply that A is closed. So and that completes the proof.